Okay, we're live. Hi, everyone. So I'm very excited to introduce, I guess, two sets of talks today around basically this Mega-kernel compiler project at CMU. So we'll have two speakers today from the same group, Mengdi Wu and Xinhao Cheng, and they're both advised by Zihao Jia, as far as I understand. And so this talk will be focused both on the actual compiler to task representation, as well as how you actually map these things to the kernels on the GPU. So without further ado, I'll let Mengdi take it away.
Okay, thanks for the introduction. Okay, so yeah, I will introduce our work Mirage, a multi-level super-optimizer for tensor programs, which uses the super-optimization approaches to generate efficient CUDA kernels. Okay, so GPU is the most popular domain-specific hardware for executing machine learning applications. But GPUs are complex, which has multiple levels of computation and memory hierarchy. And on each single GPU, there are tens to hundreds of compute cores, which are called streaming multiprocessors. And each SM contains hundreds of CUDA cores. And all these compute units can run in parallel, which forms a complicated design space of parallelization strategy. Moreover, memory at different levels have different bandwidth, sizes, and accessibility. Generally, the memory at the lower level has a higher aggregate memory bandwidth and a smaller size, and can be available by a smaller set of compute cores. And in order to write GPU kernels which has a good performance, the programmers need to carefully manage the tensors at different memory levels. Therefore, it is very hard to design high-performance GPU kernels. In order to perform neural networks, the existing systems usually launch kernels for individual operators. For example, here, in order to execute this computation graph, the existing frameworks, such as PyTorch, will launch separate kernels provided by the vendor libraries for each operator, such as the RMS-norm kernel, the softmax kernel, and the matrix multiplication kernels. But this may lead to suboptimal performance due to missing optimizations, such as the kernel fusion, algebra transformations, and local memory reuse. In order to achieve a high performance, people manually implement the optimized kernels for certain computation patterns. For example, here, the last three operators, matrix multiplication, softmax, and another matrix multiplication, form the popular attention computation. So people manually implement these optimized attention kernels, which require hundreds of lines of C++ code in CUDA or hundreds of lines of Python code in Triton, which requires a large amount of manual effort. And the remaining operator RMS-norm is still computed by a separate kernel. And in order to bridge the gap between this high performance and low manual effort, we introduced Mirage, a multi-level super optimizer. Mirage is not the first super optimizer or automated optimization frameworks. Existing super optimizers, such as Tassel and PAT, apply algebra transformations on the operators at the kernel level in order to find an optimized algorithm. Another category of work, including TVM and answer, they perform schedule transformation to improve the efficiency within a single kernel. However, all this work all rely on the users to define the commutation of kernels and cannot generate custom kernels whose commutation is not standard. Mirage uses a holistic approach to perform optimizations across multiple levels of the GPU hierarchy, supporting all of these object transformations, schedule transformations, and custom kernel generation. The input of Mirage is a tensor program, and the output is a set of optimized GPU kernels to efficiently execute the input tensor program. Mirage requires less engineering effort, where we instead of writing thousands lines of CUDA code or hundreds lines of Triton code, you only need to write a few lines of Python code in Mirage. And it also performs better performance. It also achieves better performance, where in our benchmarks, Mirage outperforms the existing systems by up to 3.3 times. And moreover, Mirage is easily adapted to new architectures and new models, where we do not rely on any manual implementation. So, in order to achieve the holistic optimization, let me first introduce our IR, the Mugraph, a multi-level graph representation. Mugraph captures the hardware memory hierarchy with multiple types of graphs to represent commutations at each level. Specifically, there is a single kernel graph in each Mugraph, where the vertices represent the commutation running on a kernel on all the SMs of a single GPU. And the edges represent the intermediate tensors stored at the device memory. The vertices can either be standard tensor operators, such as matrix multiplication and or reduce. These are all supported by vendor libraries. And in addition, we also have a special type of operators called graph-defined operators. The commutation of these special graph-defined operators are represented by a lower level graph, which are called thread block graph. Which are different from the kernel graph is that the vertices in a thread block graph represent the commutation of a single SM, and the tensors are stored in the shared memory. What is similar to the kernel graph is that we can also have standard operators supported by vendor libraries and graph-defined operators whose commutation is defined by an even lower thread graph. Operators in the thread graph are computed by a single thread, and the intermediate results are stored in the register file, which are similar to the kernel graph and thread block graph. And with this Mugraph representation, Mirage is capable of representing optimizations at multiple levels. And the challenge is, how do we explore the extremely large search space? A common approach is to define a set of transformation rules that maps a subgraph that match a certain pattern into an equivalent one. For example, here in the first rule, we reorder the division and matrix multiplication according to the commutativity between division and multiplication. And the second rule applies the for loop along the reduction dimension of a matrix multiplication. And this is a scheduled transformation. So this transformation-based approach is good for optimizations within one level, because in this case, the transformations can be summarized as limited rules. However, if we consider this a multi-level optimization, the problem becomes hard. In this multi-level optimization, the most important one is custom kernel generation. And on the input, in this case, on the input side, we can fuse arbitrary operators into a single kernel, which means we can have infinitely many possible input patterns. And on the output side, we don't have common rules to generate optimized kernels because the optimized computation can be very complicated. And therefore, the transformation for custom kernels are dense and irregular, and they're very hard to design. So Mirage instead uses an exhaustive search. It takes as input a tensor program and performs the exhaustive search to generate all the possible Mugraphs up to a bounded size using exhaustive search. And these generated Mugraphs are not guaranteed to be correct. So Mirage next uses an equivalence verifier to check whether the generated Mugraph candidates are correct by using random testing and we have theoretical guarantee on the correctness of this. And all the verified Mugraphs are sent to the Mugraph optimizer, where we perform optimizations that do not affect the correctness of Mugraphs, such as tensor layouts, memory planning, and operator scheduling. Finally, Mirage will pick the fastest kernels as the output. So let me first go into the Mugraph generator. In the Mugraph generator, we first maintain a library of operators at all the kernel, thread block, and thread levels, serves as the primitives. And Mirage will exhaustively search for all the possible Mugraphs using available operators up to a certain size. For example, here we see from the input there are three input tensors. So we start from a graph with 3 input tensors, and we try to generate the first operator, which can be a matrix multiplication, an exponentiation. It can also be a graph-defined operators. And then Mirage will try to generate the second operator. It can be another matrix multiplication, or if we encounter a graph-defined operator, we will try to generate its underlying computation definition by generating the lower-level graph using a similar approach. In this way, we do not miss any opportunities to optimize the computation. However, the search space would be extremely large. And our idea is that we use expression-guided pruning. From the input tensor programs, we can derive the desired expression we want to compute. For example, here the input tensor program is RMS norm followed by a matrix multiplication, and the desired representation is like for each zk equals the summation over wki times normalized term. So during the search, we can use this desired expression information to guide the pruning. For example, in the first branch, we compute the e to the power of xi, which means all the following Mugraphs must contain it as a sub-expression. And here we assume that there cannot be any redundant computation in the optimal graph, which means this e to the power of xi term cannot be cancelled in the following search. So however, in the desired expression, we see that there does not contain any exponentiation. Then we know that this branch is useless, and we can just prune it out. In the second branch, the current expression is not directly a substring of the desired one, but is actually a sub-expression of the desired one up to some basic abstract properties. And there can be an expression that is equivalent to the desired one, and also contains this yk as a substring. In this case, we keep this branch and continue exploring it. This expression provides good things for pruning. However, full information expressions are still too complicated to reason about. So in order to achieve a good balance between the pruning quality and pruning overhead, we introduced this abstract expression, where we, instead of keeping all the detailed informations in the full expression, we abstract away the index details. For example, the commutation of a matrix multiplication is Cij equals to summation over k, aik times bkj. And here we abstract away the index details, and this expression becomes summation over 64 elements, and each element is entry from input tensor A times entry from input tensor B. And we can recursively compute the abstract expression for a Mugraph. Yeah, we just pick random variables, random and distinct variables for the input tensors, and we compute the abstract expression for a tensor from the semantic of the operator that generates this tensor. Yeah. So by this abstract expression, we can capture most of the semantic information. And these abstract expressions are also easy to reason about.
I actually had a question.
Okay.
And there is one in the chat I'll get to. So like, do you need to have these algebraic expressions beforehand, like fed into the system? Or can you feed in like a Python script and it converts it for you?
Yeah, that's a good question. So we will take the user does not need to provide this abstract expression. So the user only need to provide the PyTorch or Python Python representation of the computation graph, and Mirage will automatically derive this abstract expression and use this information during the search. That answer your question?
Yeah, and then I guess the kind of follow-up is in the previous slide when you do the pruning.
Yeah.
So are there like I'm like unfamiliar with this, but like are there solvers that basically can do this kind of sub expression solving thing for you? Like in my head this seems quite expensive, but maybe I'm thinking about this kind of naively.
Yeah, that's a very good question. Yeah, actually, yeah. So this can be represented by in any like solver, the proof system of any solvers, but if we directly encode this full expression into solvers, it would be very hard for the solvers to resolve this problem, and the solving time would be unaffordable. That's why we take this abstract expression approach. So this would simplify the logic that we require from the or we require the solvers to support. Actually, yeah, we have explored we have tried to that the solvers to directly solve this full expression. Yeah, but it's very slow, and that's why we try to simplify the representation. Yeah, so this is a trade-off. If you give more to the solver, then it's more automated, but the solver would become very slow. And so instead, we can handle something. We can find the structure from the commutations by ourselves, by the system designers, to simplify the tasks for the solver in order to get the result in an affordable time.
I see. There was also a question in the chat. I'll ask the closer one first and then the other one. They're basically saying like in the next slide, when you define the like, yeah, this expression, they're saying it seems very similar to Einsum notation. And they're asking like, is there any relationship between them? Or can you use Einsum notation here as a replacement?
Yeah, I think it's very similar to this Einstein representation, and we capture. I think we capture a subset information of the Einstein abstraction, and we can absolutely use use Einstein abstraction as a expression as a replacement, and I think the reasoning would be the similar. So. I think what matters here is that how do we use this representation to help us prune the search, and how do we perform our optimizations on top of these representations. Yeah, so I think this abstract expression or Einstein representation can both work.
I see. There was a question from like a much earlier slide, I think, where you were talking about basically like operator optimization, but they were saying like, I don't follow why there are infinite patterns. It was a slide about like why you need to do this like decomposition in the first place. I think it's even earlier.
Earlier? Which one?
This one. I think it was this one.
This one?
Yeah.
Oh, okay. Can you say the question again?
Well, the question was, I don't really follow why there are infinite patterns. I remember there was a line that said something about like there are infinite patterns that come out of this that you have to search for, but I don't.
Okay. I think for infinitely patterns, I think it's this slide, if I understand correctly.
Oh yes, sorry. Yeah, I see it.
Yeah. This slide. Yeah, the point of this slide is that, so if we want to generate custom kernels, so we need to transform part of the. So if we use this transformation-based approach, we need first. So first, we don't know where to put the operators. For example, we may if we have like 3 operators, operator 1, operator 2, and operator 3, we may want to have a kernel to compute the operator 1 and half of operator 2, and another kernel to compute the half of operator 2 and operator 3. So in this way, it's very hard for us to design the transformation rules because there's not a clear boundary of this cutting space. This is one point. And another is, once we so in this transformation-based, in the traditional transformation-based approach, we only have limited rules, because not every pattern of the computation can be transformed to an optimized one. However, in kernel generation, we can always fuse arbitrary operators into a kernel. So that's why we can have infinitely many possible patterns. So basically, you can think of this transformation as a function from the subset from all the subgraphs of the input tensor program to another subgraph. And in this custom kernel generation, this function is very dense, which is in contrast to these traditional transformation-based approach, where the transformation is a very sparse function. Yeah.
Perfect. Thank you.
Okay. Yeah. Thanks for all these questions. And I will continue to. Yeah, and we'll continue to introduce how do we use this abstract expression to guide our search. So we will build a set of axioms which are represented in first-order logics to reason about the abstract expression relation. Here we have 2 sets of axioms, these equivalence axioms and these sub-expression axioms. So these equivalence axioms capture the abstract properties between operations. And note that here we only need to reason about the algebraic properties between these simple operators, where we only have this like addition, multiplication, division, and summation. And these are all scalar, all in scalar granularity, which means this equivalence axioms is very simple compared to the like abstract algebraic properties related to tensor computations. And these sub-expression axioms basically are just reflexivity and transitivity. Okay, so this is the full pipeline of this abstract expression guided search. Here we take as input the input tensor program, and Mirage automatically derive this desired abstract expression from the input tensor program. And then we do the exhaustive search. In each step of our search, we will compute the abstract expression of the current partial Mugraph and use an automated theorem prover, which takes these equivalence axioms and abstract expression and sub-expression axioms to prove whether the this abstract expression for partial Mugraph is the sub-expression for the desired one. If the answer is yes, then we just continue the search. Otherwise, we will prune out this branch. And we have some experiment results show that this abstract expression can actually significantly improve the scalability of the search. Here, the blue line shows the search time for the Mirage without abstract expression, and the orange line shows the time for Mirage search with abstract expression. You can see that after 6 operators, if we do not perform abstract expression, we cannot get the answer in affordable time. And in our example benchmarks, the Mugraph needs 11 operators. Okay, and that's all for this Mugraph representation, Mugraph generator and abstract expression pruning. And the next component in Mirage is this probabilistic equivalence verifier. So the Mugraph generator will generate a set of Mugraph candidates, but the correctness will not be guaranteed. Now remember that in our pruning, we prune out, we abstract away some informations, and that may lead to some mistakes in the outputted Mugraph candidates. So we need a verifier to check whether each generated Mugraph is actually functionally equivalent to the input tensor program. And our idea is to use random inputs, random testing basically. And in order to avoid this numerical issue, we run all this random testing in finite field. So basically, we randomly generate the input tensors for both the generated Mugraph and the input tensor program. And we evaluate 2 graphs on the same input and check whether the outputs are the same. And we have theorems to prove that if G1 is equivalent to G2, then O1 always equals to O2. And if G1 is not equivalent to G2, then with a certain probability, O1 does not equal to O2. And this gives us the probability of this false positive. Yeah. And next is the Mugraph optimizer. So in the Mugraph generator, we only consider the optimizations that does not alternate this output, which include these algebra transformations, kernel instantiation, and compute organization. And these optimizations can all captured by the Mugraph. And for other optimizations that does not affect the correctness of a Mugraph, or we can say that which are not captured by the Mugraph representation, we will defer these optimizations after we verified the Mugraph. And these optimizations include tensor layouts optimization, memory planning, and operator scheduling. Yeah, in this way, we reduce the generator search space and solve the rest of the problems. Yeah, since they are more orthogonal to each other, we solve other remaining optimizations optimally. Yeah, and that's let me show the experimental result. We evaluate Mirage again. We evaluate Mirage on these subgraphs selected from the popular machine learning applications, such as normalized transformation, QK normalization. This QK normalization means attention with Q and K being normalized. And this RMS norm plus matrix multiplication, and the group query attention, LoRa, and gated MLP. Our baseline include all of the vendor-provided libraries, expert-written kernels, and compiler-generated kernels. We can see that Mirage can outperform the existing approaches in most of the cases. Yeah, finally, let me show a case study to demonstrate Mirage's ability to discover hardware customized Mugraphs. So in this, for the group query attention, Mirage can generate a kernel that is similar to this expert-written implementation, which is flash decoding on L100. And here we need 2 kernels because the first kernel computes some partial sums, and we need a second kernel to accumulate these partial sums, because we cannot directly communicate between thread blocks in a single kernel. And in H100, since we have new architectures that allow us to communicate between thread blocks, so we leverage this GPC level or reduce to accelerate attentions. And Mirage would automatically leverage this feature to generate efficient kernels. And actually, it is 2.2 times faster than the best existing kernels. Okay, finally, let me summarize. So Mirage is a multi-level super optimizer that can perform algebra transformation, schedule transformation, and new kernel generation together, where we only require minimum engineering effort, and we can also achieve high performance. And Mirage is an open source project. Our paper is submitted by the OSDI this year, and if you are interested, you can contribute to our repo. That's for the Mirage. I can take some questions.
Thank you, first of all. There was a question in the chat, and then I think we can ask ours, and then we can go on to the next slides. But the question was basically like, can you help give us some intuition or like understanding for how the system would discover something like a tiled matmul? And basically like, how does the way that you're dealing with these like algebraic sub-expressions and stuff help find like the extra summation terms for tiling?
Okay. Yeah, so let me maybe go to the... Okay, maybe just use this one. So, okay, so for tiled matmul, tiled matmul is a very simple commutation. And in order to discover the optimized commutation for tiled matmul, Mirage maybe would try to let's assume this is the best one. Actually, Mirage will try to explore all the possible ones and pick the optimal one. And one of the solution might be Mirage will generate a thread block graph, which takes as input the matrix A and the matrix B. And it will try to generate these input iterators. So here we comes to a detailed design of the Mugraph, where we use this input map and output map to represent the. So there are some parameters in the for the thread block graph called grid dimensions and block dimensions, which are the same in the GPU in the CUDA programming term. And we also have this input map and output map to show how to represent how do we map the tensor dimension to this grid dimension. And here for all these hyperparameters or this non-graph structure parameters, we will enumerate all the possible values for them. This is very expensive. And it's actually the current bottleneck of Mirage. And here we use some heuristics to help us reduce the search space. And we also have some ongoing project to try to reduce this cost. And by exploring all the possible input maps and grid dimensions, we try to Mirage is able to represent all the possible tiling or blocking strategies for tiled matmul.
Thank you. I'm quite curious, like, my understanding of the system is you're doing exhaustive search over some set of like operators or optimizations, and then you're effectively like the way that you check that they work is you just directly check correctness by running it in some way. So like, how long does this compiler actually take for like, let's say like an attention snippet or something?
For our benchmarks, these 6 benchmarks, Actually the slowest one is the LoRa because it has the number of input tensors is larger than others, and other than this LoRa, for other benchmarks, our search time is within 30 minutes or 20 minutes, and for LoRa it may run several hours, like 3 to 4. Yeah.
I see. And like roughly how many, I guess, like attempts does it make, like per like if you give it some function and you ask it to optimize, like how many candidate solutions does it come up with usually?
It varies a lot across different benchmarks. Generally, it can have up to hundreds of candidates. I think for most of the benchmarks.
I had a question, which was like, I'm sort of curious, like, as you were looking at what those like outputted kernels look like, did you find them to be particularly human readable? Do they look like they were generated by a compiler? Any comments on the readability and lines of code of the outputs here?
Yeah, that's a good question. So there are two levels of outputs of Mirage actually. So first it is verified Mugraphs. So the Mugraph representation is very human readable because it's mostly about the strategies and the generated CUDA codes. So for the outputs we have generated CUDA codes that would not be that readable because for example the tensor names are not related to their semantics. But for the Mugraphs, it is very readable, and we also have a visualizer to visualize this Mugraph.
All right, very helpful. Thank you.
There was another question. Oh, you go first.
Yeah. Okay. Yeah, I do have a question of like about the search space. Like, I'm quite curious. Like, how big do these graphs get? Like, I imagine that for some stuff, like as you said, Aurora, these graphs can get pretty insanely huge. So, like, what's the rough number of operators and so on? Like, did you check that? And like, how does it? So, like, for example, how does this number of operators correspond to the speed of the kernel?
Yeah, that's a good question. So yeah, I just have some high level intuitions, and I'm not sure whether they're actually true or they're the only aspects affecting the efficiency of search. But from my experience is that so the this abstract expression pruning is very good at pruning the non-correct or useless graph structures. So the main cost of the search is on those aspects that cannot be efficiently pruned from abstract expression, such as this parameter tuning and the input. So input enumeration. So for LoRa, there are 4 input tensors for the in the input tensor program. So we need to in our search, once we generate operator, we need to enumerate its inputs, and this is very expensive because once you add one more operator, the complexity goes exponentially larger. So yeah, that's my intuition.
On with the last 2 questions in the chat, and then we'll move on. So the first one is, can you speak to implementation details not mentioned in the paper? And basically, if you were to implement like this system for other hardware vendors, like TPUs or AMD GPUs, would this work out of the box, or would you need to do other stuff? And basically, like, is it device agnostic?
Yeah, it's a good question. So in order to support, let me go to the another. Yeah, in order to support other other backend platforms. So yeah, so first that the For most of the hardware platforms, the memory hierarchy is actually very similar. They all have this multiple level of memory hierarchy. We have device memory, and we have on-chip memory, and very local memories. This is very similar across all of the machine learning or domain-specific hardwares. So this Mugraph is generally capturing these optimizations across multiple devices. And what we need to modify is that here we maintain this library of operators at multiple levels. And this may need to be re-implemented to adapt to other platforms. But this might be very simple because we assume all these platforms have these own kernel libraries for us to use. And another might be this solution is general, and for the parameters like these grid dimensions, block dimensions. In other platforms, there might be other parameters and may need different heuristics to generate. Yeah, that are two points that need to be re-implemented in order to support other hardware platforms.
And then in the interest of time, I'll do one more question. We can kind of circle back to the ones after. But basically, this person there's like kind of two parts to this question. The first one is more specific. It's like, do you have a system for discovering that threads in a thread block are sharing memory? For example, collaborative reading into thread group memory for tiled matmul. But broadly, what they're saying is this Mugraph search is all over algebraic transforms. So it's not entirely clear to them like how this actually maps onto the hardware. And like the software kind of abstraction that, say, like CUDA provides.
I see. Yeah, if I understand this question correctly, I think they're more about the details of this Mugraph optimizer or the transpiler, where we transform. How do we transform this Mugraph to a CUDA program? Yeah, so this Mugraph is mostly designed to capture the optimization strategies we want to the programs need to consider during their work, and and to transform a Mugraph into a CUDA program, we just do we just do some string manipulation. Yeah, so we have a transpiler that uses some uses some traditional compiler approaches to transform Mugraph to the CUDA program. And also, these optimizations, these Mugraph optimizations are also included in this transpiler.
Got it. Thank you. I think we'll go on to the next talk, and we can circle back to some other questions after.
Okay.
Perfect. Okay, take it away.
Okay. Hi, everyone. This is Xinhao, and I'm going to introduce follow-up projects based on Mirage. In this project, we're trying to compile the entire large language model into a mega-kernel. So since we already have some background from Mengdi's talk, so I will skip this kernel part. So for LLM serving, most of the existing systems using a kernel per layer approach. Each layer in the computation graph is implemented in one CUDA kernel. For example, model layers may have matrix multiplication, multi-head attention, or reduce, and all these computations are implemented as matmul, attention, and or reduce kernels. So we already have a lot of techniques to implement and optimize these kernels, such as cuBLAS, flash attention, flash MLA, Nico, and something else. So in this kernel per layer approach, each kernel includes multiple thread blocks. The thread blocks are going to be dispatched into different streaming processors on GPU to do computation. So it is very hard to do workload balance in a static way. For example, the amount of this computation of attention kernels are depends on the KV cache length. So in this case, each streaming processor may perform computation for different requests, and some of the requests may be much longer than others. So as a result, attention computation on some SMs may be much longer than other SMs. In such case, other SMs are idled for a long time when the last block hasn't finished. So in a static way, we cannot do optimization since the workload depends on the real data. We need to wait for the real request comes and performs balancing for the workload. So there are several limitations of the current kernel per layer approach. First is that there's no interlayer pipelining. In this traditional approach, kernel serves as a barrier. So for example, in this case, we have attention kernel followed by reduced kernel. We rely on the kernel to guarantee that the computation is in the right order. Because we launch the reduced kernel and the attention kernel on the same stream, it means the reduced computation cannot start before the attention kernel finished. This kernel barrier prevent us from software pipelining across different kernels. For example, we can start the data loading for the next kernel before the current one hasn't finished. But this software pipelining is hard to implement in this kernel per layer interface. The second limitation is it's hard to overlap the compute and the communication. Kernels capture the data dependence in a very coarse-grained way. In this case, we have all reduced kernel followed by, we have multiple kernel followed by the all reduced kernel. If we look into the data dependency, so each thread block of the all reduced kernel only depends on the thread block, only depends on one thread block of the matrix multiplication kernel. But if we launch them as separate kernels, all reduced computation must wait for all matrix multiplication computation done before they can start. So this kernel per layer approach prevents us from overlapping the computation and communication. Finally, for CUDA programming, it is very important to use CUDA graph to reduce the kernel launch overhead. But CUDA graph is a static graph, which is hard to support dynamic workloads. In today's LLM serving, we launch hundreds to thousands of kernels for inference. So this results in a significant overhead. So kernel fusion is a good way to address this issue. We can fuse multiple kernels into a single kernel. In this example, we have a matmul followed by we have an RMS norm followed by a matmul kernel. In this case, we can apply some algebraic transformations, which has been introduced in Mengdi's talk. We don't need to compute the yi. We can directly use the 3 input tensor to compute the final output z by reorganize the way we compute. Through this way, we only need to launch a single kernel, and we have better software pipelining. And also, we reduce the device memory access since we don't need to read and write the intermediate result of this yi into the off-chip memory. So here the question comes. Kernel fusion is very desirable. So is there a way to push kernel fusion forward? Can we fuse everything into a single kernel? The idea is instead of launching hundreds to thousands of kernels to compute the layers of the LLM, we can launch a single mega-kernel to compile and compute everything. In this case, there's no longer kernel barriers. And also, we can reorder operators. So as we discussed before, each all-reduce only depends on one piece of the matmul. So it is safe to reorganize the all-reduce and the matrix multiplication, and we can still get the correct result. This reorganize allows us to achieve compute and communication overlap. When some of the streaming processors are using the tensor cores, others can do all-reduce and utilize the NVLink bandwidth. So this approach also let us get better load balancing. For example, for attention commutation, some SMs may finish early, so we can assign more works to these SMs to reduce the overall latency. So to summarize, this mega-kernel approach provides 3 key advantages over the current kernel per layer approach. First, we have better interlayer pipeline. We have better opportunity to build software pipeline between different operators. And we can also overlap compute and communication because now we capture fine-grained data dependent. We know each piece of this all-reduce only depends on one piece of the matmul, and we can reorder them, and also we maintain the correct result and get overlapping between with this different GPU resource. And this also provides better support of dynamism workload because we no longer need CUDA graph. When everything is fused into a single kernel, the kernel launch overhead is minimized. So we can build a runtime system to handle this dynamic workload. So Mega-kernel is very desirable since we fuse everything into one kernel, but this is also challenging. The first challenge is that we need to manage the data dependencies. Originally, we rely on kernel barrier to handle this dependency. Now, without it, we need a new mechanism to make sure that the dependencies are still preserved. So the second challenge is handling the dynamism. For LLM serving, there's many degree and dimension of the dynamism. For example, it is very common to use continuous batching, means that we batch requests from different users together and serve them in a single iteration. We may have different number of requests and different number of tokens per iteration. Sometimes we may need we may mix the prefill and decode phase together. It is also very common to use page and radix attention, and sometimes we use speculative decoding to reduce the latency. So all this approach introduce different degree of dynamisms. So the last challenge is to optimize the performance. Since most of the existing compilers optimize the individual kernels, but when we fuse everything into a single kernel, we care about the end-to-end performance of this whole kernel. So we use 3 techniques to address these challenges. First, we use task graph to manage the dependency, and we build an internal runtime system to handle the dynamism. And finally, we use the super optimizer to generate highly optimized kernels. So our system is called MPK, which means Mirage Persistent Kernel. You can think we have a compiler, and the input is a LLM architecture, and the output is a highly optimized mega-kernel. Our compiler can reduce the engineering effort. Users do not need to write thousands lines of CUDA or Triton code. You can just provide the Python code of your model, and the compiler can generate mega-kernel for you. So MPK also gives high performance. Our kernel can outperform existing service systems by 1.2 to 6.7 times. And we also offer day 0 support for a new model. You don't need to add a new CUDA code for your new model. So MPK has 2 main components. It has a compiler and a runtime system. The compiler takes LLM as an input, and and also some of your serving config, such as how to do batching, paging, and speculative decoding. And the compiler will generate a task graph. Once we have this task graph, it can be used by the MPK runtime to serve requests. And here is the task graph definition. So this task graph interleaves tasks and events. These are the two definitions in our graph. In this figure, the blue box, each of the blue box is one task. One task is a unit of workload that runs on a single streaming processor. It can be a computation task, such as a tile of matmul, one head of attention. It can also be a communication task, such as transferring a piece of data to another SM or transferring data to another GPU. In addition to the tasks, each of the green circles is called event. An event handles the synchronization among tasks. So in this figure, an edge from a task to event means that we need to notify the event when the task is done. And we also have edges from event to task. It means that when the event is fully triggered. So fully triggered means all tasks the event depends on are finished. At this point, we can launch all tasks that depend on this event. So we are going to explain this further on a later slide. Task graph is similar with CUDA graph definition, but in CUDA graph, each node is a kernel that runs on entire GPU. In our task graph, each node is a task runs on one SM. Task graph is a lower level of CUDA graph. It takes a sub-kernel dependency instead of an entire kernel dependency. So a task graph is also static and immutable. We construct it once and repeat it many times while serving. So first, we want to talk about the compiler. MPK includes a compiler that converts the original model architecture to a task graph. So the compiler can optimize how we map the layer to tasks, decomposition based on the number of available streaming processors. So the compiler also automatically adds synchronization events to capture the task dependencies. For example, for all-reduced task we talked before, each of the all-reduced tasks only depends on the one piece of matmul. So in this case, we have events connect each pair of this all-reduced and matmul. So this allows us to capture the data dependency at the finest granularity. Finally, we automatically generate CUDA implementation for each task. So after we generate a task graph, the graph will be executed on our runtime system. The runtime system have two kind of roles. We have schedulers and workers. Each scheduler runs on a warp of an SM. One SM has 4 warp executors. So it means that we can serve 4 schedulers in one SM in parallel. We run the worker on one SM. So in our design, most of the SMs are reserved for workers. We only need 1 or 2% of SMs as schedulers. So our runtime system is a task-based runtime. So each worker has its own task queue, and each scheduler also has its own independent event queue. So each worker will repeatedly fetch a task from the queue and execute the task and notify the event when the task is finished. So on the scheduler side, it will also repeatedly dequeue this fully triggered event. The fully triggered events we have talked before, it means that all the tasks it depends on has finished. And it will launch all tasks depending on the event. So for now, let's use a demo to show how this runtime system works. So this follows the figure on the top right. So first we have initial events that's not depending on any task. So it means this event is considered already triggered, and it can launch all tasks depending on this event. So this scheduler will launch these 4 attention tasks on different workers. Once the first attention task is finished, the worker will notify the event. Because in this task graph, each event depends on 2 attention tasks. So it means that this event must be notified twice to be fully triggered. So there's nothing to do now. So once the second attention task is finished, it will notice the event. So for now, this event is notified twice. It is considered triggered. So once this event is triggered, it will handled by one scheduler. The scheduler will launch 3 matmul tasks depending on this event. So similarly, once the other attention tasks are finished, the corresponding event will trigger and launch the subsequent tasks. So this approach let us gradually launch all tasks and handle all events, while still maintaining the data dependency. So this approach also allows us to run the all computation inside a mega-kernel. So we compare our end-to-end performance with the existing service systems such as Torch, VLM, SCLN. So this figure shows the performance of serving Q13 8 billion on a 100 GPU. We can reduce the per token latency from 14.5 milliseconds to 12.5 milliseconds. For LLM serving, there's a hardware limitation. Since we have to load and store things from device to on-chip memory, so the serving latency is bounded by the memory bandwidth. So according to the bandwidth, theoretically, serving a token on A100 takes about 10 milliseconds. So our mega-kernel approach pushed this software performance towards the hardware limits. So our project is now open source in the same repo with Mirage. So it's joint efforts across many organizations, and we are now actively working on the following up project. And we welcome any questions and contributions. Thank you.
Thank you. Mark, you want to ask first?
Yeah, so I think there's one thing that wasn't too clear to me, which was when you mentioned an intra-kernel scheduler. I was wondering if you could elaborate a bit more on how this works. Like, and just for context, like, you know, on my end, what I'm used to is like you have a PyTorch program, you figure out like some sort of intermediate IR, and you generate like kernel code. That's something I understand quite well. So I was wondering if you could speak like in more detail about the scheduler story.
Yeah. So let me. Yeah. So if I'm can I explain this example? Do you think that may help you to understand?
So what I meant is more like I'm not too sure like how this looks like at a code level. Like basically, like are there like specific, yeah, like the sort of high level picture makes sense. I'm just like wondering what does the end level kernel end up looking like? Because you do mention like a CUDA kernel eventually gets outputted, and is it like the CUDA kernel is aware of all of these things? In which case, I'm curious what that looks like.
Yeah. So this scheduler is that we use a warp as a scheduler, and so it maintains a queue on this scheduler, and we just when there's it's fully triggered, it will like we will enqueue a new we are going to pull out this events from this queue and then notify the other SMs. So this the detail is that we just write something to the device memory, and so let other streaming processors know that that there's something changed in the. So there's a loop inside this schedulers to fetch things from the workers, and inside the worker there's also a loop to catch any changes in that worker.
All right, maybe if after the talk, if you have time, do you mind just like sending me a link to that like loop that you're referring to? I'd be very curious to see what it looks like.
Yeah, I'll send you via on Discord or
That sounds great. Thank you.
Email. Yeah, sure.
Yeah, I was also quite curious about that, in that like it seems like the scheduler or like the warp is just treated as just like a single threaded imperative program. Like, do you use the other threads in some meaningful way in the scheduler, or do you just treat it like it's just running instructions one by one?
Yeah, that makes sense. So we use a warp since that the instructions are executed in a warp level. So actually we only like run one instructions to write this to the device memory. So but there's no difference to use one thread or one warp. So we use one warp.
I see. There was a question in the chat. Paul is asking, I think in one of your examples, I think that RMS norm plus the MLP or like linear is not fusible under tensor parallelism. Yeah, this might have been a previous slide.
Yeah, let me see. It should be.
Yeah, maybe I'll elaborate on this question as well, because so it wasn't really clear to me if are like redistributions also fused in the kernel, because like I think typically you want to be interleaving like tensor parallelism for the MLP, but then sequence parallelism for RMS norm. And so like do you also fuse the redistribution, and sort of any details on comms might be helpful.
Yeah, so if this fusion that's like introduce more communication, we are not going to like use this in our kernel.
I think the question might have been with regards to another slide, by the way. Maybe one more.
Sorry, which slide?
Yeah, maybe one more here. All right, so it seems like the answer here is that like you would just like you wouldn't use sequence parallelism basically, right? Like you would just like basically insist that everything continues to just be pure tensor parallelism. You eat the extra memory cost, but then you don't just redistribute comms, and you can keep a mega kernel. Is that right?
Yeah, I think so.
Okay,
gotcha. Yeah, another question is in JAX, autodiff is implemented via source level transformations that can be lowered to the XLA compiler. Do you think in principle Mirage could be a substitute for XLA as a compiler in the future?
Yeah, I think for now our target is to provide a general compiler for all tensor programs, and we are also working on this engineering efforts on supporting more kind of like tensor programs and also more hardwares. So yeah, actually we are our target is to cover this LLM serving stack, but I think yeah, that's our goal. So we are going to compare with all these serving systems and see what's the difference.
So one thing like that's quite common in a lot of like compilers is that like before you decide to fuse something or not, like you basically will just run the fused versus unfused variant and see what's faster. And typically, I've heard in the past that like the reason why mega-kernels weren't popular was because you run into like inherent like register spillage problems. So I was wondering, how does your approach deal with this? Like basically when you should not fuse, or and because like I think especially mega-kernels also kind of became popular as people were fusing entire small models, but obviously people weren't fusing large models, and I'm sort of curious if you could comment more on all of this.
Yeah, I think that's also some engineering problem we have encountered. Like so sometimes at the beginning we use a if else to separate these schedulers and workers. So but that cannot, so because in the workers we use a lot of registers, but in schedulers actually we don't need that many registers. But if we use a if else condition, that the source code that does not split this register allocation for different for schedulers and workers. So for now, we separate this scheduler and workers into different kernels and use a green context to do this to do this communication between them. So for now, we get rid of these registers. And for a kernel fusion, I think we are currently we are using this based on our intuition. It's like we develop different sizes of kernels and fusions, and we test the performance of the single kernels and also the register things, and we select the best one.
There was an earlier question, which also applies to Mengdi, if you're still here. But is there a tracer or logger or some kind of visualizer where we can see the entire process of search and transpilation in Mirage? Or like some kind of open tool for this?
Yeah, is Mengdi still here?
Can you hear me?
Oh yeah.
Yes.
Yes.
Okay. Yeah. So so currently we only have some statistic results statistic numbers during the search. Yeah, we don't have like this tools to help the for it. We only have the visualizer for the Mugraph. There are still some limitations of the search, and we have some ongoing project to improve them. So it's still under this rapid development. It's not. We don't think it's stable enough for us to have a visualizer or logger.
Okay. I think that should be it for this. But thank you guys so much for this wonderful talk. I think it was super, super interesting. That should be all. So thank you guys for coming. And yeah.
Thanks again, folks.
Thank you.
For coming.
Thank you.